So Kate did a very nice introduction. I will have some overlap, I'm very sorry, but I will try to have a different angle. So I think probably we will have different questions. So I'm going to start with a very broad introduction. So just to say where we come from, in some sense. So first thing is just to take the age of the universe. When we think about the Big Bang, everything started something like 13.7 billion years ago, and then we had this big evolution, the building of the galaxies, and then at about something like 4.5 billion years ago, then the birth of the sun, our sun. And then, so in our context, when we're trying to understand the formations of the young planets, we are really focusing on something that is happening right now. So just at the time of the formations of stars that were from 10 to 100 million years ago. Okay, so that's the time scale. Now going to the scale in terms of size of the universe. So if you take one very small and dark piece of the sky, and you take one of the most amazing instruments that mankind has ever built, Hubble, that's what you see. It's dark, but it's not completely dark. So you see a lot of point sources, and they are all galaxies. Okay, and then if you pick one of these of those galaxies, like the spiral one, like the Milky Way, that's what you will see. So billions of stars forming this galaxy. So what you have in the universe, you have billions and billions and billions of stars. Now, when we're trying to study planets and to image planets, we're really focusing, on the very close neighbors, close to our sun. So if the universe is the Earth, in our case, we're just, watching the neighbors, so really close, the house is really close to us. Okay, so now, Kate said that, a bit. Our sun is not completely, the average star that you find in the universe. If you plot, the various sizes that you find, as a function of the mass, actually, the most, important populations of stars are the Loma stars, what we call the M dwarfs, and they are the ones, that are everywhere in the galaxy and in the galaxies that we have in the universe. Okay, now, so when we are studying, planets, so we are focusing really on the stars that are really close to our sun in our galaxies, and we have these two families of planets, the giant planets, where it's really difficult to walk planets, and the terrestrial ones. And then, by definition, the exoplanets are planets that are located around other stars. Okay? Then we have this plot. So, this amazing introduction. So the log scale. So we see exactly the same kind of thing. So here, the mass is given as a function of the mass of Jupiter. So you see here Jupiter, and then the distance is given as a function of the astronomical units, which is 1 astronomical unit is the distance between the Sun and the Earth. And so on that plot, after 30 years of observations, hunting planets, that's what we found. And so you see a lot of diversity. As you actually answered, there is a blank space just over there related to the instrumentations we're using. And the thing which is important is, okay, we see that we have some overlap, with the planets of our solar system, with the population of exoplanets that is observed. But if we were trying to observe, a solar system like our own, we will just see Jupiter. We won't be able to see what is hidden, in the system, like the terrestrial planets and the other, giant planets of the system. That's something very important to keep in mind. Something which is also very interesting in our solar system is we have terrestrial planets, one belt, the asteroid belt, giant planets, and one other belt, which is the outer belt, which is the Kuiper belt. Okay, so we have a very specific architecture, and something which is very interesting for us is to try to understand if this specific architecture is something which is a prerequisite for the formation of life. Okay, so big questions we have: how will we form the giant planets? How our solar system fits in this zoo that we are actually observing? And if this architecture that we find in the solar system is something very important for the emergence of life. That's a big question that we have here as astronomers during this conference. Okay, so what I'm going to do now, I'm a ground-based astronomer, so I'm completely biased by the instruments and the telescope that we're using, on the ground. And so I'm going to focus on 2 observatories in Chile, because I've been spending 5 years of my life in Chile. I just came back like a few months ago. Okay, so Chile, Chile, and in the north of Chile, you have one of the most amazing sites for astronomy, and you can find 2 observatories. ALMA, which is devoted to the observations of the cold parts, of the universe, and then you have the Paraná Observatory, which is like 7 hours driving from ALMA. So ALMA is particularly interesting. So you have at 5,000 meters in the Atacama Desert. So here it's like super dry, no clouds, almost no humidity. And then you have this network of antennas that is observing the universe. And you have 64 antennas. And then these are the first images that I got of these baby solar systems. So focusing on one star-forming region. And what you see, the big surprise, was to see a lot of structures in those systems. So you see rings, you have, in some cases, you have spirals, you have what we call vortices, so overdensities of materials. And here, so this was one of the big surprises. So we see that, young baby solar systems, where you see the dust, you see a lot of structures that are probably created by the birth of planets that are just forming. Okay. Here you have the typical size of our solar system. And then something that you can do, in addition to study the dust, you can also study the gas, which is located around the star. So thing that we also was very interesting was to see by spectroscopy that you have a lot of molecules, and you find some kind of molecules that are actually pretty complex, like what we call organic molecules, that are the first bricks for the emergence of life. And this was done less than 10 years ago. Okay, now switching to Paraná. So here, again, I'm super biased because I'm using this planet imagers here. But here the goal is to take a direct image, as Kate was showing for various cases. And here you're combining various techniques. So you just want to take a picture of a planet which is actually orbiting a nearby star. And so you're using, because you are from the ground, what we call first adaptive optics, just to compensate the effect of the turbulence, coronagraphy, to block the lights from the star, and then some differential techniques to try to remove the instrumental artifacts. Okay, so you have this 4 steps. This would be like the kind of image of a star that you would see at the VLT, 8-meter telescope, so it's a bit disappointing. Then you close the adaptive optics, so you can restore the quality of the image. This is what you have. So you're just imaging your star. And here you have the contrast that Kate was mentioning, which is the typical ratio between the noise in your image and the peak, the maximum peak of your star. Then you're blocking the light, so you're putting your coronagraph. So you're gaining a factor something like of 10. And then you're using this differential tricks that we're using just to remove all the residuals that you have from the instrument. So this kind of what we call speckles that are mimicking actually the signature of a planet. And then you can resolve your nice astrophysical scene. So here is a beta peak system. So the light of the star has been completely hidden. Then you see the nice debris disk, which is a kind of dust, circumstellar dust that is located around the star. It's seen edge on, so that's why we just see a line. And then we have to resolve the planet, which is actually responsible for the warp that you have in the debris disk. Okay, so here I'm going to focus on one super interesting system that has been super exciting for the astronomers and the direct imaging community, which is PDS-70. So this system that has been observed with ALMA, and here what we see is a very nice outer belt, which is very similar to the Kuiper belt of our solar system, but the system is just forming, something like, I would say, 5 to 10 million years. Then what you have in the middle is what we have a kind of inner belt, which would be kind of similar to the asteroid belt. And then what you don't see for the moment, and that you will see in the next image, we have 2 planets that have been imaged actually in this system. So this is the sphere image of the same system. So you see again the outer belt, which is this kind of Kuiper belt. Inside you have the inner belt. Here it's not completely hidden. You have a planet B, a planet C. And so you start to see something which is very, very similar to our own solar system. Outer belt, giant planets, inner belts similar to the asteroid belts. So the next question is what you have inside. So clearly, this system is super exciting because you just find a kind of similar architecture to our own solar system. So now the big question for us, we have one system like that, and what we like to understand is how many of those systems are actually present in the star-forming regions, to really try to understand really this connection between outer belt, giant planets, inner belt, and then the presence of terrestrial planets. So one of the big steps for us is to go with these extremely large telescopes that are just now starting to be built. So you have various projects on the US side, on the European side, and they are starting. So construction has started for the EMT, which is 39 meters telescopes, in the north of Chile for the European community. There is a webcam, so you can actually see what they are doing now, just the construction. Everything is supposed to start in 2027, so this is the ideal landscape. Of course, it's not going to happen. I mean, we are going to get delays and so on. But yeah, this is going to be a game changer for ground-based astronomy, and to go inside this inner region where we want to search for these terrestrial planets and really to try to understand the origin of our own solar system. I will stop here and take questions. Thank you.
Great, thank you. It was a very interesting talk. So are there any questions? There must be some.
It talks about the plane of the planets around the stars. The image was shown had to be head-on, right? The plane.
Yes.
That one, yeah, exactly. Is there an ideal position to observe the plane? Would you rather observe it head-on, or maybe?
That's a good question. I mean, for the planets. You don't care because in some sense, the planet is point-like. But what you see here, one problem is that you can have at some point, the light of the disk, which is superimposed to the light of the planets. Here, the planet is super bright. This planet is something let's say 10 Jupiter masses, so much brighter than the disk. When we are pushing, to go to lighter planets, then you can have another one. So this is one problem. And obviously, when it is edge on, you're accumulating everything, but it's one problem, okay? When it's polar, it can be nice. It's actually what you have here, for instance. But then you can have, for very young systems, a lot of structures in the system. And when you look at this image, here is really point-like. Here we know, and there is another image where you know that it's a second planet that is hidden. But you already see that it's very difficult to disentangle the signal that is coming from the disk and the one which is coming from the planet. So it's something very critical for us. When you're observing young stars, you have material from the disk and you have the planet which is hidden. The more you want to look for the planets, for faint planets, then you're going to have this problem of contamination from the disk. So, it's difficult. And you need best thing to do is to have various criteria, various observations to disentangle the two things.
What I understand is that you try to put the way the solar system is onto the other analysis. Yeah. That is a match that you can find a match. And you have a nice example there where you show, okay, there is an outer ring, there is planets in the inner ring, and then there's of course what is in the inner ring.
Exactly.
Do you have more of those examples, or is it only one example that?
So yeah, the question is, do we have more examples than the one I showed, so PDS-70? At this typical age, we have one, but we hope we can get more. So, because this is a very, as related to your question, it's really difficult at these very young ages to disentangle the signal coming from the disk and the one from the planets. Okay. Then for systems that are a bit more evolved, then so the gas is going to dissipate, the dust also is going to be removed slowly. And then we have a bit more, not so many systems, but I would say 5, 6, where you can see this double belt architecture, and the giant planets. Okay, then the question of the terrestrial planets. Currently, we don't have images of terrestrial planets. This will become like the next generation of ground-based instruments or space telescopes. More questions? Yes?
How do you decide what stars are good targets for direct imaging?
Sorry, how do you decide what is a good target for direct imaging? So, in direct imaging, I mean, it's exactly what Kate was saying. We have two limitations. We have the fact that what we want to detect is really close to something very bright. So we need usually to have like big telescopes, to access to this small angular separation. But what you can do is to pick stars that are very nearby. So the distance of the star is something important. And the second aspect, so there is a contrast between the star and your planets. And when the planet is young, it's actually hotter and so easier to detect. So that's why we are focusing on young systems. So we say that we're focusing on young nearby stars. That's a typical key targets for direct imaging. This maybe is going to change with the reflected lights. So you want to observe like superverse. You want to be sensitive to the reflected lights of these planets. And then with very large telescope, we probably are going to change this paradigm and to just observe very, very nearby systems to be sensitive to these reflected lights. Yeah.
Are there any benefits of ground-based telescopes to space telescopes? Like, why do we even use them? I mean, you can just build a bigger and better space telescope compared to ground-based.
So, so there's like various aspects. I mean, for instance, the ELT is 40 meters. We are, for now, it's like not possible to build, one mirror, one segment of this size. And so here, I mean, the technology, we have to cut everything in small pieces. The ELT has something like 800 segments. So you need to align everything, co-phase everything, and then you have to hold, the dome and so on, the infrastructure. So, I mean, for this size, yeah, we have to do it from the ground, and then it's less expensive. To have this kind of telescope in space, we don't have the technology to do so. I mean, the biggest telescope that we have is, so now it's James Webb, it's like 6.5 meters in space, and I mean, it has been like extremely difficult, in terms of technology, budgets, and so it's very complementary. We have to see that it's complementary to go to space and to actually do also this kind of science from the ground. When you speak about direct imaging, for instance, many discoveries came from the ground because we had this ability to build the large telescopes and then to have this kind of versatile instrumentation. One thing with space also is you have to think 20 to 30 years in advance. And during that time, the technology is changing a lot. From ground, it can be 10 years, 8 years, and that's enough. So if you have a clever idea, then you can put it on the telescope like 5 years after. So that's why I think we have to think it's very complementary. And then, the ground is feeding space, and space is feeding the ground. I mean, see, this is a question for ESO.
Why not just ESO?
I mean, for ESO is like organizations like taking care of the European telescope in Chile. And the plan is to have very broad instrument as first light, that doing everything, and and a bit of like direct imaging of exoplanets, but not at the level of performance where we could image super-Earths, for instance. And why? Because I think they are super conservative. I mean, for ESOs, the first time there will be segmented telescopes, so this is like a big thing for them, I mean for us. And so yeah, I mean they're trying to do like some kind of very instrument that can do a bit of everything: cosmology, galaxies, solar system, and a bit of exoplanets. But yeah, I mean that's a pretty good question. I think that more like because they're conservative and they want to wait to that we got some knowledge about the telescope so that we can push for a second generation of like more specific instruments. Because clearly, I mean, imager of like terrestrial planets, it's a kind of niche, for the community.